this clear? Everyone can hear me? All right. Well, thank you everybody for coming to my talk. I know it's early on day 3 and we're all getting a little tired. Today I'm going to speak to you about my research on optimizing quantum transport in open quantum systems at the University of Toronto. All right, so when I say quantum transport, I'm using this just as a catch-all term for any transfer of quantized particles between coupled quantum sites. These particles could be electrons or charges. I'm thinking in general just about excitons, and bosonic excitons at that. Quantum transport occurs in devices like solar panels or quantum computers, and there are many applications where we might want to optimize transport when we think of a system design. And that's the point of my research, is I want to tune the on-site energy splittings of my system such that quantum transport is maximized through it. All right, so the system that I'm interested in is just a one-dimensional chain of 2-level systems, and I'm specifically going to assume that only one exciton can be present in the system at a time so that I can use this tight binding Hamiltonian you see here. I'm going to talk about 2 different coupling schemes here. The first is just on the left, nearest neighbor hopping only, so I'd use the Hamiltonian on the left there. And then on the right, I'm thinking about a fully connected model where I can have hopping from any site to any other site, and the hopping strengths are given by a power law model. I'll talk about long-range and short-range coupling. And when I say that, I mean alpha is going to be equal to 1 in this power law coupling model for long range, and equal to 3 for short range. Right, and these on-site energy splittings are the parameters I will be trying to optimize. Since the session is called Open Quantum Systems 3, I'm going to hope that everybody is familiar enough with open quantum systems. I can just speed through this. But when I say open quantum system, I mean a system that is interacting with its environment. And this environment could, for example, be an infinite number of harmonic oscillators. I'm going to assume that the interaction between my system and its environment is weak so that I can use the Lindblad-Master equation. I'm also assuming that my environment is Markovian. As I'm sure many of us know, the Lindblad-Master equation can be split into 2 terms. This first term, the commutator, is the unitary part. You can obtain this just from the Schrödinger equation, and it describes the coherent dynamics of my system. And on the right, the second term is often called the dissipative part. This describes how the bath dissipates excitations in the system. I'm going to specifically use a pure dephasing model for my dissipator. I'm also going to be interested in studying the steady state of my system over the dynamics, which I obtain just by setting this equation equal to 0. All right, to mimic a real system where I might see transport like a solar panel, I'm going to assume that there's a population current through my system, and I'm creating this current by letting excitons leak out of my last site at some rate gamma. And to maintain a unit trace of my density matrix, I'm going to re-inject the excitons at the same rate into the first site, once again, to have a current. In this scheme, I'm defining transport efficiency just as the flux of population through the last site. So that is eta equals gamma, the rate at which excitons are leaking, multiplied by the steady state population of the last site. And this eta, this transport efficiency, is the quantity I'm maximizing with respect to the system energies. To do the optimization, I'm using gradient descent. So gradient descent is possibly the most intuitive optimization technique I've ever used. It's basically thank you. It's just if you can picture yourself standing on a hill, you look at the hill, figure out which way is uphill, and then you step in that direction. And you do this over and over again until you reach a flat slope. I'm specifically using optimistic gradient descent implemented with the library OptAx because I found it worked well with my complex efficiency landscapes in parameter space. And I'm calculating my derivatives of efficiency with respect to the on-site energy splittings with the JAX library, both of which I can direct you to at the end of the presentation if you're interested. This is going in the wrong direction. There we go. To start off, I looked just at 3 site systems because, as I'm sure we all know, only the energy differences impact the behavior of the system. So with 3 sites, I only have 2 independent energy differences. And to simplify things further for the optimization, I fixed the first site energy at 0. If I have nearest neighbor coupling only, that's here, maybe I'll try the laser pointer out. With nearest neighbor coupling only, you can see here on the left in orange that the optimal energy profile for transport is this flat orange profile, which isn't too surprising or exciting. I found, though, that with all-to-all coupling between my 3 sites, that I get this V model that optimizes transport in 3 sites, which we figured out is just the system wants to promote transfer directly from site 1 to site 3, and site 2 is just getting out of the way. You can see here on the right, these are the steady state populations of my system, and I have a very clear population gradient from site 1 to site 3, which is good. That's what we want. We want to promote the flow of population from 1 to 3, and we have a decreasing slope to have that happen. Now, for longer systems, the picture is a little more interesting. This example is a 10-site system, again with the pure dephasing bath. Here I looked only at all-to-all coupling, both short range, so power law with alpha equal to 3, and long range, power law with alpha equal to 1. Here, the orange, the short range, you can see, like with the 3-site system, it's very flat, kind of bowl-like. And the populations decrease linearly, again, which is what we expect to see. We want to promote transfer down a population gradient. However, the long-range system has this very distinct oscillatory pattern, and I'll tell you, this is the optimum. I tried many different initial conditions. I redid the simulation over and over. This is the profile that came out every single time. You can see how there's like a local maximum here at site 5. Site 2, again, is very out of the way. And I do have a decrease in population through the system, but it's not the linear decrease that we expected. So if I look at the steady state coherences in the site basis of this 10-site model, we can deduce some explanation of why these are the optimal profiles. Oops, it went back. Here on the left with the short-range coupling, probably unsurprisingly, I see strong coherences between adjacent sites, and I think you can see on the screen too that there's like some weaker coherences between next nearest neighbors, which leads us to believe that, yeah, the transfer is just hopping from one site to the next through the whole chain. On the right, though, the long-range coherences are much more interesting, and I've put, oh my gosh, and I've put the energy profile here on the top right as well. Was there some feedback just there, or am I hearing things? I'm good? Okay. Right, so you can see how there's little to no coherences between site 2 and all the other sites, which isn't too unsurprising given how much farther away site 2 is in energy compared to all the other sites. You can see though that site 1 has strong coherences with every other site, but specifically sites 5 and 6. there are strong coherences between sites 1 and site 5, and also strong coherences from site 1 to site 10. There's also generally stronger coherences like in the second half of the system with site 1 versus the first half, like sites 6 to 10 have stronger coherences than like 2 to 4 with site 1. If I look at site 10 as well, there's a strong coherence with the first site and also with the last site, and it kind of increases as you approach site 10. So we think that the transport pathway that occurs here is transfer from site 1 to 5, then 5 to 10. Oops. All right, so in conclusion, you may have noticed generally that my first site and my last site all have the same energies. That's a distinct pattern, but also that strong long-range stay-state coherences persist in these long-range coupling sites. Next, I'm going to consider more thermal baths and some higher dimensional systems. I'd also like to acknowledge the governments of Canada and Ontario for their funding support, as well as Professors Dvira Siegel, Juan Karaskija, Eric Gauger, and my colleague Matt Pockernick at U of T. All right, thank you.